옛날에 봤던 거. 18년, 15년 될 것 같죠.
Okay, so let's get started. Announcement. Next week, we won't have lectures. Okay, so we will have to arrange a makeup lectures or 2 makeup lectures. So I'm thinking of using midterm exam period to have to make lectures during that. Let me know if that doesn't work for you.
First, you could extend the lectures until 5 today.
Till 5 today. No.
It's possible literally.
Why is that? Oh, there's nothing after this.
Yes.
Okay, good to know.
So I mean not today, but I mean it's also an
I mean,
option.
that's an option. Very good. So Tuesday, who has a schedule right after like our regular lecture? You have. So there's that option. Anyway, so for now, then let's just say that we're going to have 2 mega lectures during midterm. The same time, same room, but we can check whether that works. Okay, so with that, any questions from previous lectures?
아, 근데 생각해보니까 저는 청강이기 때문에 네, 저거가
Still, we value 31st. Yes. Okay, any other comment? But if that is the only available option we have, then we will just push on that. But since we have other options, okay. Okay, good. So since there are no other questions regarding previous lectures, let's continue. So far we talked about representation of Lorentz group. We sort of understood how to organize, how to think about representations of Lorentz group, which is basically so everybody, please send an email. I mean, even if you are registered, you're welcome to send an email, say hi. I'm here again. See you. Okay. All right, so we've been talking about representations of SL2C. We learned that it is organized as S plus S2, basically 2 copies of 2SU2. Okay, modulo some important technical details, but that's basically that. And then last time we talked about how to think about the vector representation very quickly. Since the dimension of this representation is 4, right? Also, since this guy had a dimension which is equal to basically product of the 2 SU2. And then also by importing the fact that this is real, also it preserves parity. And recall that under the complex conjugation or parity, we saw that basically that can be incorporated as exchanging J minus and J plus, or equivalently S plus and S minus. So by importing these 2, we learned that we're looking for representations where S minus or plus is equal to S minus in such a way that 2S, if I call that to be just S, in such a way that 2S plus 1 squared is equal to 4. So that uniquely select out that a vector representation is equal to F and F. Okay, so that's what we talked about. One thing that that is interesting and good to know is the following. So if we look at the rotation subgroup of SL2C or Lorentz group, by which I mean, we know the following. So rotation, for instance, if you look at the rotation around an axis n10 by angle theta, it is generated by e to the minus n generator, which I call L, I believe, and theta. But in terms of this language, we saw that the angular momentum or rotation generator is same as the sum of the two SU2 generators. Which means that in this language, if I may just rewrite, for the sake of being totally clear, here J plus, J minus, and then beta. So if you look at this equation, first you say, of course, but hopefully you also appreciate the fact that this equation captures the following fact. Rotation is generated by a sum of the two SU2, right? Sum of the two SU2. And when you have, or it is actually sum of the SU2 generators, which means that as a group element, it is the same as so rotation is under direct product representation of two SU2s. Is that clear what I just said? Okay, it's the sum of the generator, so it is a direct product representation under in terms of group element itself. So therefore, you see that this by this I mean this is equivalent of thinking as it's a product representation basically. So it's there schematically, and then you know what to do. So here it basically said that for SU2 representations, if you have a direct product representation, you do have, by which I mean direct sum from differences of two to sum of the two, and then you have entire this direct sum decomposition, right? That's what we talked about. Why am I mentioning this? I mean, this is a useful thing to know, and nice way of thinking about the rotation group as a subgroup of a rotation, Lorentz group, but also for this vector representation, if I just constrain myself to the rotation part, just for the sake of it, then this discussion tells me that the vector is decomposed once again, because I have to think this as if it is a direct product. So then this gives me that it should have both sum in terms of rotation, and then 1, right? So okay, that's good, because now this one has a 2 times 1 plus 1, which is a dimension 3 object. This is a dimension 1 object, which we expected to be dimension 4 object, which is the vector representation. In particular, this shows that under the rotation, vector representation is decomposed into spatial 3 vector and then scalar. Okay, and this will come up again when we talk about vector field and then gauge invariance and so on. So that's what we talked about. Let's talk about the tensor now. And then we will talk about Fermion after this. We will spend maybe 2 weeks or longer on this Fermion. So tensor, for instance, let's talk about something that looks like a 2-index tensor, like so. Okay, so the goal is to understand this in terms of that language. So this schematically, so this tensor schematically, again, can be viewed as this product of 2 vectors like that, right? If you like, you can raise the index too. So therefore, let's first understand that in terms of that representation. So I have 2 vectors, which we have understood what vector is in this language. So it's a product of the 2 vectors. There is a 1, and there is a second. Okay, now you know how to do this. This is equivalent, by which I mean I can do the similarity transformation to diagonalize it into the black diagonal form. This is equivalent to a bunch. So there's a direct sum decomposition. Let's add up. So that's 1, 1. And then I can go down. So first add up and then subtract. So that's a 1, 0. And then the other way around, so 1. Finally, 0, 0. So naively, this tensor product, if you look at it, the dimension of that thing is going to be 4 times 4, because I have index of each of the vector It runs from the 0 to 3, which is 4. So that's 16. In other words, there is a, if I just write a tensor like that, it is a representation matrix acting on the tensor, which is the 16 by 16 matrices to rotate all those 16 degrees of freedom. Okay? So anyway, so now going back to this language, so let's check the first of all dimensionality, and then let's understand better. So this one has a 3 times 3, that's 9. That one has a 3 times 1, that's 3. That one has a 1 times 3, that's 3. This is 1. If you add up, you must add up to 16, which checks, first of all. But let's understand slightly more deeply about the properties of these representations. So we talked about exchange symmetry. So if I have two identical vectors, suppose I had a vector, and then I just constructed two tensor out of the same vector. Okay, then it makes sense to talk about. So what I'm saying is that if these were constructed out of the same vector, like so, then I can talk about exchange symmetry, right? So, and then we say that for SU2, top spin representation is symmetric. This is symmetric. This is symmetric. Next one is antisymmetric. So this is antisymmetric, symmetric, antisymmetric, antisymmetric. Right? So we talked about that. Now, overall, this 1,1 representation is symmetric because I have two indices. Under the exchange, it's a +1 times +1. It's symmetric. And this is antisymmetric because this picks up the +1 side, this picks up the -1 side. Then again, this is antisymmetric, this is symmetric. So it looks like the tensor representation can be decomposed into a symmetric to tensor and an antisymmetric to tensor. Okay, so that obviously we are familiar with. Let's write it in a more conventional tensor expression. So here's a tensor, which I know can be decomposed as a symmetric tensor and then antisymmetric tensor, like so. So symmetric part, without needing to write, but I'm nevertheless writing, is this part, and the antisymmetric part is this one. But understanding tensor in terms of this language actually tells us immediately something more than just decomposition into antisymmetric and antisymmetric, right? Because even within the symmetric, there is two subcomponents, and then even within the antisymmetric, there are two other subcomponents. So we can try to understand where and how this decomposition happens in terms of this more conventional tensor analysis language. Okay, so that's the thing we can do, and then we can move on. So let's first try to tackle the question of a symmetric tensor part. So symmetric tensor part, again, in the tensor analysis class, whatever kind you had, you just forgot, right? You had it somewhere in here, there. So let me get that out of your memory. So we learned that if I had a symmetric tensor, the difference between the symmetric and the antisymmetric is that if you look at the trace, symmetric is non-zero, antisymmetric is 0, right? That's the key difference between the two. Okay. So symmetric tensor can be decomposed into traceless part and then trace part. Let's just do it. Okay. So since I have only two objects I'm allowed to use to construct. One, this itself. Second, metric. Okay, so out of that, I have to just create, at the end of the day, an object which is symmetric under the exchange of mu and nu, and here we go. So if you are curious about, first of all, why G mu nu, because once again, other than the S, G mu nu is the only object I have at hand that I can use to construct symmetric objects. So here we go, it works. Second, what is the one for? Obviously, if you look at the trace of entire object, then since trace of G mu nu is 4, So it just knocked out that person. Okay. So therefore, we learned that the symmetric two tensor can be decomposed into traceless and then trace part. Obviously, yes.
So I keep catching that G mu is, I think, -1, 1, 1, 1. So how can I think that?
Yeah, good. So that's why I always put either here or somewhere, right? Whenever I wrote down that kind of expression, I always put this quad mod. But let's just stick to the mathematical definition of trace. The trace of metric, so I'm just writing this way, okay, is what?
No.
And which is, basically delta mu sum. Okay, so in order to see that inverse metric is inverse metric. Okay. Let me write if that makes sense to you. Inverse metric is this. Maybe inverse should go in. So if this is a metric, this is inverse metric. So this is basically 1. So I'm just writing in terms of index, this is 1. This is the delta identity matrix. Okay, and then this is the definition of trace, right? Because you contracted this one tensor with this one by, I don't know, mu, and then you had the two laptop indices also summed over. That's trace. That's the delta mu mu. Again, u is summed over. So that's why 4. Okay, good. So now let's match to that result that we got almost, free, right? Almost free. Like we just didn't do much. We just did this naive decomposition. So trace part is manifestly, single degree freedom. It's a scalar, right? I mean, there's no any other Lorentz tensor index is floating around. Okay, so this is manifestly scalar, and that must correspond to d of 0, 0. And then out of the how many? 9. I subtracted the single degree freedom, so this must be capturing sorry. So total symmetric degree of freedom is 10. Let's do whether that's correct. Okay, the dimension of S is 10. Why is that? There's a 4x4 matrix which is symmetric, right? So then there's a I have the sum 1, 2, 3, 4. Okay, so that I learned I think is a 5 times 4 divided by 2. That is 10. Beautiful. So yeah, this is 1. This is 9. That's what I'm saying. What about the antisymmetric part? Let's work that out. That's a slightly less trivial, but it will be useful when we talk about case theory. So let's do it. So what about A mu? First of all, let's recall the following. I mean, you want to basically get everything out of all these expressions once you learn. So these both are A are real, B is a parity invariant. Right? Because under the either complex conjugation or parity, remember we are just basically exchanging these two numbers. So they are both real and parity invariant. And exactly for the same reason, this is complex and not parity invariant. Okay, so then in order to understand that decomposition for antisymmetric part, we know in 4 dimensions, any parity violating tensor structure is associated with epsilon tensor. Okay, so that epsilon tensor obviously, by which I mean 1, 2, 3 is equal to +1. Any even permutation of that is 1. Any odd permutation is -1. Any repeated in this is 0. Okay, as usual. That's my definition. Okay? Why did I say that any parity violating tensor is associated with this one? Well, what is parity? Parity has to switch or turn the vector sign, free vector sign to the -1, leaving temporal being unchanged. So this one manifestly has that structure because of the fully antisymmetric structure, at least one of them needs to be temporal. The other three must be distributed into spatial kind. But since I have only odd number of a spatial kind, under the parity, it will flip, right? So it captures the parity violating effect. So we can use that to construct what is known as a dual tensor. So that I write it as star of A union. The star of A union can be defined as, so this is dual tensor. Given this antisymmetric tensor, I multiply that with epsilon tensor. And then, in order to avoid the double counting, I divide it by 2. By double counting, if I had a 1, 2, 1, 2, 2, 1, 2, 1, and then you just exchange and they pick up the same sign, so it contributes twice. That's why I want that. Okay? So in order to avoid the double counting, I divide it by 2. So let's study the properties of this thing first a little bit. Now, the one of the homework problem, only one of them. This time, you will have kind of to compensate lack of a homework problem one last semester. Okay, so we are playing non-local in time action. Okay. So if you do it twice, oh, by the way, okay. Before talking about homework problem, let's actually just look at a couple of problems. So for instance, if I look at the 0, 1, you can do it 0, 1 again to get the plus sign non-zero 2, 3, 2, 3, right? And then you have a 3, 2, 3, 2, and then because of this, you get 1. So this will be 0, 1, 2, 2, 3. You can keep doing it, right? So what do you want? 2, 3, guess what? 0, 1. And so on and so forth. Okay, so you can keep checking. So then, again, going back to this this thing. So you can check that if you do it twice. Okay, let's see. Take antisymmetric tensor. If you do once, go up, 2 times, go down. You can show that it picks up the minus sign. Just checking whether it should be up and down. I mean, it doesn't matter. Okay. Now, good. So that's useful. Oh, but oh yeah, I wrote that. Let's see if I can finish that. Yeah. So now, again, if you look at these expressions, let's see if you can extract the meaning of this expression that I will just tell you now. A star is an operation that acting on a space of antisymmetric tensor, but it will not act on a space of a symmetric tensor. First of all, right? Because of this, if you multiply by symmetric tensor, that's 0. Okay, so this is an operation, again, that acts on the space of antisymmetric tensor in such a way that star square is -1. Okay, I'm just combining this information, but let's put a word around it. So then you have a vector space that is spanned by this A mu nu object. There is a morphism or operation acting on it with this this property. Okay, then whenever you have this sort of structure, then you can ask, oh, can I reorganize my vector space in terms of eigentensors of stars? And then rewrite arbitrary 2 tensor in terms of that basis tensors. Okay, so that means that we should have So because of those things, we say, okay, can I then possibly, so because, can I say that there is a eigen tensor, which I put plus minus there. But since this is an eigentensor, as I told you just now, you see that if you're squaring it, obviously you're going back to yourself, right? Okay. So, okay, actually, let me write slightly better. I mean, it doesn't matter. Let me write just a little bit better. So lambda plus minus. How about that? So I have a eigentensor with that property, which means that lambda equals to -1. And there are two choices. So basically, I could have written already that star of A plus minus acting is a plus minus I this. Suppose I can construct such an eigentensor, then I can hope that I can rewrite this arbitrary two tensor in terms of those two eigentensors. All right, good. In fact, it is quick to see that you can convince yourself, because anyway, there's 12. Let's see if I get this right. So the claim is that this is that expression. Okay, so in terms of that, and then dual of that, or you can invert this relation easily, right?
Do you write I twice?
Yeah, I think I wrote I twice, and I meant this.
Okay.
Thank you. Yes. Let's check. Star of a mu nu is that. Please do it.
Professor,
Yes.
I think covariant and contravariant notation is mixed because of the star operation.
Say it again. Oh, you mean the this versus up?
Oh, no, no.
What did I do? Sorry, say it again.
주얼주의 문호가 위로 올라가야 될 것 같은
Well, I can always define the other way around. I can just put it down and then put it down and put it up. So I can do the other way around too. Or I could have written everything with the up indices.
주어를 취하는 거에서 아래 인덱스를 가져온 거 아닌가?
Well, my notation is this.
바로 밑에 보시면 그잖아요. 기호를 하면.
You mean to go up and down? But if I do it twice, I'm coming back to it. Right?
듀얼에서 위에 인덱스는 원래 있던 거에 아래 인덱스로 가져온 건데 저건 듀얼 한 거에서 아래 인덱스 거로 가져온 거니까 원래 거에서 보면 위에 인덱스게 되겠죠.
Sure. Okay, I understand. Okay, first, yes, let's clarify. You can get whatever you want as the answer. Let's see. If I want to have a dual with the up, obviously I will use the up indices epsilon tensor with the down index to tensor. If I want to get the dual with the down index, I'm going to use the epsilon with the down indices with the up to tensor. Vice versa. So, but since I want to define an object with the down index mu nu, I'm just rewriting in terms of both the down indices. But again, if you like, what I meant is again half epsilon mu nu sigma A. Okay?
어디 헷갈린다 할 것 같은데. 스타 한다고 위아래가 바뀌진 않는데 바로 밑에 A 0에 스타 있는데 아래로 내려가는 게 저는 좀 헷갈렸었거든요.
Oh, good. So there is a relative minus if that's your question. So for instance, if you're asking whether this versus relative, then you're asking whether this is the same as that or there's a relative minus sign?
아니. 그러니까 0일 앞에 스타를 붙였더니 2, 3은 아래로 내려갔잖아요.
Yes.
그러니까 저는 스타를 붙이는 게 위아래를 뒤집는 게 맞는지 아닌지에 따라서. 근데 위에 로테이션에서 안 바뀌는 것 같아서.
So I literally did this job, first of all. But obviously you can, if you want, you can rewrite this in terms of ugliness too, with the matrix. Especially with the two spatial, if I raise twice with the all minus sign together, it's the same as that.
감사합니다.
Yeah. You can just go back and forth. So, yes.
Let me see first of all, we can make a rolling the index.
Yeah.
And the row indices 0, 1, 3, 1, 2, 3, 4 is not dimensions.
It's not dimensionless.
Yes.
Sorry, say it again. What did you just say?
Echelon
This is not dimensionless, is this what you're saying?
in the open list, it seems like dimensionless. So
Okay.
that is just 1 for 0, 1, 2, 3.
Yes.
But for the row indices 0, 1, 2, 3, 4, 0, 1, 2, 3 is not the dimension.
You're worrying about the square root of the metric factor?
Yes, maybe.
Okay, but if I take the Minkowski, that's 1.
Okay.
Yes. Yeah, I mean, technically you're right. There's this, this is a tensor density, not a tensor, and so on. But again, if I work on the point space and time, also. Yes.
제가 간단히
There's is there minus plus?
그거는 그냥 조이니까 상관없어요. 조이니까 뿔마가냐 막부리가.
Yeah, okay. I mean, there can be minus sign. So anyway, the point is the following, okay? So what we are doing is that according to this language of understanding representation, looks like antisymmetric tensor has to be decomposed, right? And then we want to understand that in the language of a tensor, right? And then what we notice is that, again, borrowing from the knowledge here, these representations separately are not a pair invariant and real. So we ask, okay, in this language, how do we construct a peri-violating object, which is the 2 tensor? And then we notice the fact that in 4 dimension, we can use the epsilon tensor to construct such an object, right? And then we notice that this epsilon, this is a dual operation, actually the space of antisymmetric tensor. So we can ask for a eigentensor, and then we can decompose now by literally inverting this relation. You can decompose this into a sum of these two, okay? And each of them correspond to either one of these two. So here is quickly another way of viewing the exact same thing. Okay, so I literally have done everything, but now one way to view this thing is the following. Although minus sign, so I like the minus sign. I mean, I don't like the minus sign, but that's fine because we can flip. Either way, you have to suffer. Okay. Either way, you have to suffer because nothing is consistent. Art of the physics is about the sign. So here we go. But what I was trying to say is this. So this can be viewed as F1 plus minus I star acting on A mu. And then if you view this as projection operator, which is exactly this subject, you see that if given 2 tensor, I can construct a projection operator. If you studied the Fermi already, this literally looks like F1 plus minus gamma phi. Okay? And then you can project out a part into the plus and minus, again, according to what is the eigenvalue under the star. And in the context of fermion, which we will develop, so don't worry if you don't know about it. That's exactly how we divide the given Dirac vector into chirality plus and minus things. Okay, so this is literally the same thing, but we are just doing for a tensor. Okay, so in each of that correspond to either of these. So you see that this one has a dimension 6, right? Because it's antisymmetric 4x4 tensor, and then obviously you divide it by 2, so each of them will carry dimension as everything is.
For me, is that such a hierarchy in the second to
spin 2 field. So this actually has a spin 0. Sorry, spin 1. Okay, so this one actually has a spin 1, not spin 2. And it makes sense because the photon can be represented with a field strength tensor, which is F mu nu, symmetric to antisymmetric to tensor. So it captures information about the spin 1 field rather than spin 2.
Can you do the same thing to the metric tensor so that you just something do like for gravitational waves?
Indeed, you can decompose 2 by 2 symmetric levels. I guess we talked about it here. In fact, either energy momentum tensor or metric in a generic sense, you can always decompose into, at the very least, this part, but you can further decompose this traceless part. Okay, by imposing extra condition, and then that extra condition will single out the gravitational wave part.
So then does that? Then that is not irreducible, right?
That is not
If you
irreducible.
can decompose it further. So,
You mean this?
Yeah, so you will get 9 plus 1, but by your statement, you're saying that 9 is part of the decomposable?
At least at this level, it is an irreducible representation.
Okay.
So for instance, in the context of gravity, I don't know how much you're familiar with, this may correspond to dilaton attribution, and this is a tensor gravity part. Yeah.
Okay.
So it's called the, and this part can further be decomposed into, traceless. There's this, this can be further decomposed into purely tensorial part and vector part simply. So overall, it's called the SVT decomposition in gravity.
So then in terms of Lorentz group, that is not part of the decomposable, but if you try to use additional structure, then that is decomposable.
So here we're only dealing with isometry of flat space and time. Obviously, if we actually want to talk about gravity, here I'm just borrowing only structure or similarity. I'm not actually doing gravity because I'm doing everything in flat space and time. But if you go to the flat space and time, the correct thing to deal with is diffeomorphism rather than Lorentz or Poincare group transformations.
Oh, okay.
I'm saying that there's a proper decomposition one can do consistently with this diffeomorphism.
Okay.
Yes. Okay, so that's all I wanted to say about the Lorentz transformation, a representation of Lorentz group, and we will move on. Talk about Fermion. Okay, so it's not a separate subject, right? So we just talked about, we've been talking about representations. This corresponds to chapter 19 of Coleman, called the derived equation. So yeah, so far we've been talking about the representation of Lorentz group, but we have not been talking about the minimal dimensional representation. We only talked about the vectors and tensors, right? I mean, as I just demonstrated. So the question is, what is the smallest, minimal, or if you like, or smallest okay, and who are they? That's the question, right? So it's clear because we are now masters of Lorentz group. So obviously the answer is it's gotta be either that or that. Well, I lied. You can in principle talk about it. So, but I'm skipping this because this is already included, right, in the discussion so far. So for now, let's just focus on this to top line. And then let's first understand who are they. Okay, and then we will construct eventually quantum field theory that's transforming under these representations. Okay, so let's first understand who are they. So in order to understand, what we need to understand is if there is any object that's transforming under these representations, what is the spin? How they behave under the boost, right? Those are the Lorentz transformations. Okay, so let's recall that the rotation, again, generator is the sum of the two, and the boost is minus I times the difference of the two. Okay, so then, first of all, what that means is that you take spin half representation of the first SU2 factor, that means I have this. And then for the second one, just to be totally clear, you take a 0, right? That's what it means. And for obvious reasons, you take 0 here, then you take half of sigma. That's what it means. So from this data, you can see that L, which is the sum of the two, is L of sigma, which is according to the spin half representation. So this is the same. Same for one. Representations. So object that gets transformed under this, transformed the exactly same way under the spin half representation under the rotation, right? That's what it means. What about the boost? So if I just write down this expression, that tells me that it should be minus plus I sigma over 2. So now it's different, right? Under the boost, the guy that lives here behaves differently from the guy that lives here. Okay, so it's clear. So now, therefore, let's assume, so consider now, therefore, two-component object. Eventually, we'll turn into a field, which I denoted as a U. It's not very nice. U plus minus. Once again, if I turn it in the field, eventually this will be a function of space and time. But for now, I'm just gonna take that as an object. Okay, so this is a two-component object. But to be totally clear, what I meant was, for instance, if I have a U of alpha, this carries an index, which is obviously SU2 index, which has a two components, so it has a one and 2 indices. Okay, that's what it means. And then if I have this guy, it has also SU2 index, but just to differentiate the space where this guy lives from the space where this guy lives, by which I mean to differentiate the SU2 that acts on this guy from the SU2 that acts on this guy, I will just use a slightly different notation for the index, alpha dot, which also runs from 1 to 2. Okay. Now, there is a misfortune or unfortune that either the book screwed up or I screwed up, that it's not consistent. So I think that what Coleman wants to call U plus an entire analysis may need to be U minus, in fact. And what he thinks as a U plus, I think should be U plus. Okay, I will demonstrate obviously along the line. So if you can spot a sign mistake, once again, theoretical physics is about the art of sign. Spot a sign mistake, that will be good. But I think I spot a sign mistake, not just one place. Entire discussion of probably 2 chapters, even more. We'll see. So eventually, why this matters, right? I mean, this is name for now. Okay, what's so important? Eventually, this is linked to the fact that this state, which I will demonstrate, will have a holisticity, which I will define some quantum number like spin minus half. And conventionally, we call a state or fermion spinor that has holisticity minus half to be left-handed. Exactly same token, this guy will have holisticity plus half. And conventionally, we call that to be right-handed spinor. Okay, so I have not shown you, I have not explained to you what I mean by all of these languages, but I'm just pointing out there might be, this like an object already. Okay, so now we're gonna spend some time to understand the properties of these guys, and then we'll construct the Lagrangian made of those guys. So that's the goal. Any questions? Okay, so then let's do it. I'm debating internally whether I should try to write U minus for all the equations that I will do now, which I think is the right thing, but I realized that this is the right labeling 5 seconds before I came into this room. So I'm debating whether I have to do it or not. But
how about writing U and then UR?
that's illegal.
Really?
That means that you will get arrested, meaning so yes, so in the literature, people write also UR, UL, and UR. So this is a 4-component spinor with the 2 MPs down to component. This is the sorry, what did I say? This is a 4-component spinor with only two top component non-zero, down component two component 0. The other way around. This is an intrinsically 2-dimensional spinor.
Okay.
So this is a vial, as we'll define soon, and this is a Dirac, or projected onto only one kind. So in that sense, but I understand also literature people use it for bond spinor. And then at some point, the art becomes, once again, like a psi, do they mean this or do they mean that or what? Like, sorting out the spinor notations and conventions and stuff. You need 100 pages of review. There is actually 100 pages long review on the spinor notations and conventions. Okay, any other questions? Good, let's move on. So for now, what have I done? So too much of digression. What I've done is that there should be this object, and then just using the definition, I just sorted out the fact that generator for the rotation is this, boost is this. Rotation same, boost different. So let's actually understand how they transform. Oh, okay. So I give you an option. I can stick to plus, and then there's a universal fits you have to do in your mind. And I have a little chance to make a mistake on the board. Or I can try this with a more than 50% chance that I will have a mistake everywhere. Which one do you prefer? It's up to you.
With a little mistake.
Okay, so I'll just stick to plus, okay? Okay, and it will look like the same equation most of the time as a Coleman, but there will be input minus signs here and there. I will point it out. Okay? So then every U plus, you may just convert it to U minus. All right, let's do it. All right, so let's understand how this guy transforms. So sorry? Okay.
아니,
You prefer the other way around?
아니요, 과제는 반대로 내면 조교가 좋아할 것 같아서. 조교가 또 뭐,
I'll let you decide. So that's fine. Okay, let's check whether you've been following me or you totally screwed up. Okay, so let's understand how this gets transformed on the rotation first. So under the rotation, around the axis defined by this, the angle, the U plus minus transforms as e to the minus I generator angle acting on the field. But since generator is the same, it's minus I over 2 sigma. What? Yes. Okay, so as expected. What about the boost? Along the direction defined by, I think I use A, and then size 5. So now, this can transform as minus I, what did I call the boost here? M, A, angle, plus minus, and this should be now minus plus sigma over 2, okay, that phi plus plus. Okay, so they transform oppositely. So far, it's a fact, but we have to learn more about that. So that's the rest of the lecture, basically. But anyway, this is 2 by 2 matrix, right? This is 2 by 2 matrix. And then I told you that this I introduce a two component object, so it will shuffle those 2 components. So U plus minus, which again 2 component object, and then we will see once we study quantization. But let me just state so that you see this more often than not. Anti-commuting field or object. These are file spheres. It is the minimal dimensional representation. One thing that you can immediately already notice is the following, obviously. So U plus U minus, just like the half zero, the 0 half, they are obviously related by either parity or complex conjugation, right? Because we talked about many times that parity leaves order of these 2. Okay, so now the next thing I want to discuss is eventually we want to construct the Lagrangian for these elements. Just like we have a Lagrangian for scalar, we want to have a Lagrangian for these elements. Okay, so the next thing we want to talk about is we want to construct given these 2 spinor representations, 2-dimensional representations, we want to construct a Lorentz invariance. Sorry, okay, that's not good. So this is not a good word. Let me replace this with either Lorentz scalar or Lorentz tensor. Why do I write tensor first before vector? Lorentz vector, Lorentz tensor. That's not it. Okay. So given that, I want to show you how to construct a Lorentz scalar, Lorentz vector, Lorentz tensor. Okay, that's good to know because once you have a d comma d1, d of a half comma 0 or the other way around, we have learned that if we do the tensor product, direct product of these 2, that it will decompose into irreducible representations according to the decomposition, right? So, and then I told you that this is the minimal dimensional representation of the Lorentz group, other than scalar. And then therefore, you should be able to construct everything else, including vector tensor, by first looking at the tensor product, or direct product of these 2. Oh, there was a homework for someone, because I keep confusing using both tensor product and direct product. I'm looking forward to that answer soon. Anyway, let's continue this. Oh, good. So before that, let me demonstrate one thing really quickly, because I told you that if I take a complex conjugate of the one of the representation, then it turns into the other, right? And vice versa. So let's understand that from this field rather than representation matrix. So before that, let's quickly demonstrate. So if I take this, for instance, and then if I take a star, so I did a complex conjugation of everything. So let's first ask under the rotation, this guy goes to e to the what? E to the, I literally take this equation and then complex conjugate it, right? That's what I do. So then if I get I over 2, and then sigma star, right? Good. But then I can use the following. So if you have a sigma star, and then you can use that, write it as, or at minus, either way, it doesn't matter. Sigma 2, by which I mean sigma y, and then sigma 2 inverse, which is the same as the sigma 2. Well, let's see why that's true. Okay, that's why that's true. So first of all, let's note the following. Oh, homework problem. Here we go. Okay, so homework problem, you can show this. So let's first use this. So that means I can rewrite this as sigma 2 e to the minus I over 2 sigma 2, right? I just rewrote sigma star appearing here in terms of that expression. That's all I did. And then I expanded, and then I just pulled out the sigma 2's out of it. Right? Taylor expansion, there's the sandwiches of sigma 2 inverse that I pulled it up. Okay? Good. So what does this tell you? This tells you that U star transforms in a representation which is equivalent to the original representation, right? That's what it is. Remember the equivalence? This is a similarity transformation. Let's do the same thing for under the boost. So under the boost, I get what? What do I have? So minus sigma star over 2. Oh, not this. A got 5. U star. Okay. Now again, if I do the same thing, this will become. I mean, this is actually equality. It's not like equivalence. Okay, because I literally just rewrote. This is actually equality. So that becomes what? That becomes a sigma 2 plus sigma over 2 a get phi sigma 2 inverse. So good. Therefore, the U star transforms under the boost according to a representation which is equivalent to how U minus transforms. Right? So this tells us therefore that U star transforms under the full Lorentz transformation in a representation which is equivalent to how U minus transforms. And that's what we wanted to show, right? So we wanted to show that's exactly what we expect. Okay, good. That's useful exercise. Let's keep moving. Okay, so now, as I promised, we want to learn how to construct these objects. So the first object I want to talk about is Lorentz vector. Okay. Lorentz vector constructed out of it. But let's first, already guess. We can make a guess how to construct a Lorentz vector out of the spin representations. Okay? Because Lorentz vector is a half and half, as we talked about. Right? And this is included in what? D of half comma 0, D of comma 0 comma half. In fact, according to the decomposition rule, it's not actually just included, it's actually saying. Right? If you look at the direct product of these two, this is the only representation that is included. Right? So what does this mean? That means that, if I start out with a U plus, in order to construct a Lorentz vector out of the only U plus guy, I need to use a complex conjugate representation of this guy, which we just talked about, which can be constructed out of this. Or equivalently, you can just use that as the Hermitian conjugate. There's extra trace. Okay?
Not you mind?
Sorry?
Not you mind?
So first I want to discuss, good, U minus the principal candidate. So the way I want to organize is that, so suppose I had the only U plus. Then I ask you, how do you construct any of these subjects first? And then next time I will hand you only U minus. Then I ask you, can you construct any of this? And then finally I give you both. Then also, can you also construct extra Lorentz scalar vector tensor if you have both of them? Okay? So we want first to the exercise with only one of these two. So I will first start with the U plus. So I'm saying this is a good candidate. Okay. So in fact, let's look at U plus dagger U plus. That it's tempting to think that this is Lorentz scalar. So it looks like you used to write an expression that looks like this to make it just a scalar object. But here, you should immediately know that this cannot be Lorentz scalar. Why is that? All you have done is that you took an object transforming under this, you took another object and transforming under that, and then just by this direct product rule, that guy never includes Lorentz scalar. So there is no way that this can be a Lorentz scalar, right? The only chance this guy have is to participate in this vector representation somehow. Okay, so let's see. So under rotation, how is this guy transformed? So let's see. Dagger, but that transforms the same way. So it cancels out. So it actually goes to itself. So under the rotation, yes, it is invariant. Okay. But what about under the boost? So under the boost, this guy goes to e to the minus sigma, because dagger sigma is a Hermitian generator. So they actually add up instead of canceling. Right? So they actually add up. So in fact, they are not invariant under the boost. Okay, but let's understand better. In order to understand, really, we need to understand better. So how is this guy transforming? So let's actually consider. Okay, before I write this, let's use this fact. Okay, so you have learned this. If you have, did you learn this? You must. If I give you sigma I and sigma j, you know what to do with it, right? There's a one thing to do, like even if somebody tries to stop you, you have to write some equation on the right side, right? There's this equal. What do you do? First, you decompose. No? No? Okay. Well, it sounds like no. This is one. And then this is probably new to you, but we will see eventually that it satisfies 2 times delta. 2-dimensional identity. Okay, good. So give me that. So half of that is half, right? The 2, yes. Very good. No, that is yes, good, yes. Right? So you have seen this equation, yes? Good. So we are on the same page. Although I could have just said that the sigma squared is equal to 1. Okay, that's right. I could have just said that, but you know more general expression. So you can use that to extend this sigma times whatever, give me some arbitrary angle like vector. This. And then you know that this is equal to sigma times of minus 5. So I did a simple, easy part. You tell me the hard part. This is, I mean, now, you know what I mean? I can. Let me do the easy part better. This minus 5. Okay, that's what I meant. Very good. So clever. And then you get sigma guided to that direction and cinch. So you have seen something like this before. Obviously, probably in quantum mechanics, most likely I was there, so this is cosine instead of hyperbolic, sine instead of hyperbolic. But that's the same. Okay, so here we go. So let's continue. That tells me the following. So that goes to, what did I just say? Cosine hyperbolic of minus 5, in this case, plus sigma along the A direction. And then sine hyperbolic of minus 5. Right? Okay. So what have we learned? We have learned that this guy is beautifully Lorentz invariant, but it's not Boost invariant. Yes? And it is not Boost invariant, but in which form? So let's remind you, if you have time at x, or energy momentum, doesn't matter, right? It transforms like cosine hyperbolic of phi, sine hyperbolic of phi, sine hyperbolic of phi, cosine hyperbolic of phi, dx. Right? This is how Boost acts, right? Looks pretty similar to the rotation, but cosine, everything hyperbolic. So now if you look at this, so this is equal to just cosine hyperbolic, and this is outcome just minus some sine hyperbolic. So this object transform like temporal component of 4 vector. There's a that times hyperbolic, cosine hyperbolic, and then but that with some sigma inserted with sine hyperbolic, right? So that means that's if I call that object I just studied, like so, and let me just write this way. Then if I hypothesize the spatial component of that as U dagger and then sigma vector U with a possible coefficient in front of it. Then in this notation, what we have shown here is that V0 component transforms as cosine hyperbolic phi V0, and then minus A hat 1 over eta times B vector. It's zero product, as you would expect. Yeah. But then, since I know if in order for this whole as a whole, like this 4 component as a whole, to transform correctly under the boost, I know which choice I have to make for this eta, right? So 0th component has to go to the cosine hyperbolic times itself plus. Nobody yelled at me. Good. That means something. Thank you. I appreciate it. Cosine hyperbolic minus 1 over eta A hat B vector. That's what I meant. So what I meant is this. So in order to have a correct transformation property under the boost, you learn that you have to make a choice that eta should be -1, right? So eta should be taken as -1 to be consistent with that transformation. Okay. So what have we learned? So in fact, out of this guy, we can construct d mu, which looks like u dagger, or u plus dagger. And then let me write it as a sigma mu bar. I will explain the notation in a minute. So sigma bar mu is 1 in the temporal component, because that is this one. Then minus of sigma matrix, because x of eta, as I showed, is to be -1. So out of the sphere representation, this is how we can construct the vector out of it. Okay. If you want, you can recall the following fact. I told this similar construction before. Back then, what I said was that if I give you a vector instead, I told you how to construct 2 by 2 guy, right? That was constructed out of like, sigma mu. Sort of similar thing. Okay. But now instead we construct this. So this is a demonstration of this method. But now I just sorted out exactly what construction has to be. Okay, good. So yes.
Professor, I'm thinking that the vector we you knew you have constructed satisfy the Lorentz invariance. Am I right?
It transforms correctly or consistently as a 4 vector. And then the question is, do I have a good choice for eta, for which this as a whole, by whole I mean this being a zeroth component, the rest being a special component, is as a whole transform consistently under rotation as well as the boost. And then under the rotation, first I showed that the temporal component is invariant as it needs to be, because rotation only acts on the spatial rotation, right? So temporal component should not move. Okay, that's the case. But under the boost, this indeed transform. But then I just captured the fact that this looks like cosine hyperbolic times original guy, and then sine hyperbolic with a minus sign importantly, and then u dagger sigma u. Right? And then I just, from that structure, I took that's gonna be the structure for the spatial component. But I just wanted to fix the coefficient in such a way that I reproduce the correct transformation rule, and the correct choice was eta equals.
Oh, because you've shown that the spatial component transformed like vector.
This?
Yes.
Yeah, so good. So that I have not shown, and that will be homework problem. That in fact, one of the homework problem is to show, I mean, it's not that it's big or anything, but just to have fun for you. Under the rotation, you can in fact check that this behaves like a 3 vector. And then also under the boost, you can check that with the epsilon equal to -1, indeed this component transforms correctly like the special component has to transform the boost. Okay, so that's the rest of the check. But I just use the temporal component to first fix, but then there's a self-consistent check you can do. Okay, good. So we construct one interesting object. So let's write it down, and then we can move on. So here is the board that I can collect according to the construction that we do. So the rest vector we constructed. So we say this sigma bar mu this, and then sigma bar mu notation was identity by 2 and the sigma. Okay, I could have recycled this thing, but I erased everything. So, but then you can ask yourself, what happened if I used instead u minus? So if I use the u minus, let me call this to be d mu. I will call the corresponding vector constructed out of u minus to be w, mu, and then the answer will be, so here, sigma mu notation is 1 and then plus. And then you can think about it. Okay, so now we learn how to construct the Lorentz vector out of the u plus and minus. So what about the Lorentz scalar? So how are we going to construct the Lorentz scalar? Let's go back to this D picture, okay? The representation picture. So if I have D have 0, right? So that's what you have. This is u plus, right? Or the other one is u minus. Again, let's ask, how would I ever get 0, 0 out of this? That's the question. So let's look at this. This should be equivalent to array 0, 0, 0. Oh, how many 0? Let's say 0, 0, and then 1, 0. Right? So therefore, looks like if I use a 2 of u plus and u minus, looks like I should be able to construct this guy and that guy. Right? Group theory tells me that there should be a way. The only part that you have to fill in is you should be creative and imaginative to figure out what kind of object you have to use to construct that. Right? That's the question. In fact, Lorentz scalar, let me give you the answer. So I think I used notation that this, for instance, carries SU2 index alpha, right? And then this guy, I can use another index alpha dot. Okay? So out of this guy, I can construct Lorentz invariant like so, by contracting this and that index. And this notation means that I raise the index starting from here by SU2 epsilon tensor. Like so. So you may have heard that SU2 group has two invariants. One is the delta ij, the other is epsilon ij. Right? And then I use that to construct the SU2 invariants. But I will give you slightly more dedicated homework problem for that. Okay? Yes.
The actually is kind of let me check it.
Let it be the symbol. You mean this?
0, 1 is equal to 1 and 1 is 0.
Yes, yes. Okay, sorry, yeah. So this is that object. Sorry, yes, yes. This is SU2 Leibniz-Zibida. Leibniz-Zibida symbol. Yes. And here too, you can do the similar construction now. So you can do alpha dot, and then starting with this means epsilon alpha dot, beta dot, beta. Okay, so we can construct Lorentz invariants, meaning this is Lorentz scalar. It is that guy.
I think u plus is 1/2 comma 0, but u minus is 0.1.
Yeah, so sure. So when I wrote this, I meant now I'm gonna do this math. Times. Right? There's also going to do the math together and then anticipate your tensor.
When you make the u minus,
Yes.
well, can I just raise and lower the indexes free?
By epsilon, just like okay. Obviously, I have not given you a not consistent. I have not given you a lecture on how to deal with the spinor indices. Which of you have studied the supersymmetry before? Okay, so very good. And often when one first studies supersymmetry, then they spend a month to learn all this index thing, okay? Why this is constructed that way when this one is constructed that way? You didn't ask that question. There's a whole rules. I don't want to open that Pandora's box. I'm happy to, but that's gotta be a whole separate single or 2 lectures.
Okay.
But yes, no, I shouldn't say but. Yes. What was the question?
So the question was in that expression.
Oh, yes.
Can I just
remember.
lower and raise them? Yeah.
Yes. So just like in the four vector, you use the method to raise lower the indices. Here, the SU2 invariant epsilon tensor plays a role. So you can use the epsilon tensor to either raise or lower the indices. Okay. And then I think I sort of prepared, going through this sort of a set of notations and how to think about this thing. We'll see. So depending on the progress we make, yes. So depending on the progress we make, I may give you, 20 minutes, pick summary of those things. But this is just to give you quickly that if you have, SU2, 2-dimensional vector, you know how to construct the SU2 invariants. I'm saying that this isn't that object. Let me just check. Oh, 수업인가요? 프레시맨 혹시 강의실 옮기겠다고 제가 들었던 것 같은데 지난 아닌가요? 안 그랬으면은 김영 교수님이 엄청 화나는 걸 봤을 것 같은데. 예. 예, 파이팅. 어쨌든 okay. So in any case, I think we should end here, right? 4 is supposed to be the time, Okay. So I didn't tell you this. Think about it. Okay. Maybe a normal problem. Maybe an exam. Okay. I don't think maybe we'll have an exam. Okay. So unfortunately, I didn't get to that part. But next time I will construct a Lagrangian for a quantum field theory made out of this and then that separately, and then I will consider theory that I have both, and I write down quantum field theory Lagrangian. Okay, so that's all for the things.
중에 이런 거 왜 하는 거야?
여기까지. 여기는 없어. 그래서 내가 없길래.
그래서 저거 약속이에요.
네?
그냥 원단은 이렇게 하고 가슴 이렇게 한 거 약속이었어 아니면 뭐 이유가 있었어요?
저는 어떻게 보시냐면